For this lesson, we'll be focusing on digital modulation. Now, we already covered continuous modulation, which is analog modulation, pulse modulation, which is analog to digital modulation. For this one, it's going to be digital modulation, which is digital to analog modulation. So what is digital modulation? Digital modulation is the process of switching or keying the amplitude, frequency, or phase of the continuous wave carrier in relationship to its binary values. Simply stated, you're converting a digital signal to an analog signal. Now, digital modulation has several different keying methods. However, we're going to be focusing on three of them: amplitude shift keying, frequency shift keying, and phase shift keying. Now, there are different modifications of these three variations. However, for this lesson only, we'll be focused on the most popular due to the variations in different PE references and books. So the first method we'll go over is amplitude shift keying, or ASK. ASK is a sequence of baseband pulses whose amplitudes are modulated to represent a message. Basically stated, if you look in the illustration below, you have a slew of ones and zeros. Every time you have a 1, you see an oscillation effect with your ASK output. And then every time you have a 0, it flatlines. Very simple and very similar to the Morse code effect. Also, amplitude shift keying is also known as the on-off keying. Now be aware, amplitude shift keying does have some downside. It has poor noise immunity. It has a low signal noise ratio. However, it is very cheap and simple. The second method is frequency shift keying, or FSK. FSK are signals generated by switching between two oscillators of different frequencies. So if you look in the illustration below, same thing, slew of ones and zeros. Every time it shifts between a 1 and a 0, you see two different frequencies on that output. Now also, signals are often referred to as tones, and these two signals are distinguished by calling them mark and space. Now, frequency shift keying also has its perks. It has high noise immunity. However, it does have larger bandwidth usage. And the last method we have is phase shift keying, or PSK. PSK signals are generated by causing the phase of the carrier to shift by a predefined amount, typically 180 degrees. Same thing, we have a slew of ones and zeros in our input, and every time it changes between a 1 and a 0, you're going to see a phase shift of approximately 180 degrees. Now, phase shift keying between all these three keyings is the most ideal out of the bunch. It has high signal noise ratio, it's power efficient, and it has a high noise immunity. Now this is where digital modulation gets very interesting. In previous lessons, we went over how to calculate or how to generate your modulate signal or in the equation for it. However, for digital modulation, it's very easy to generate a oscillated signal to turn on and off. That's very easy to do. For digital modulation, we're more focused on the actual error probability, or in this case, the digital error probability. So on this slide, we have error probability, the bit error rate, the energy per bit, and the bit energy, which is kind of the same thing. Error probability is the amount of errors per total number of bits received. And provide a simple equation there, bits times the probability gives you the number of errors. That's a pretty simple equation. The bit error rate is the number of bit errors that occur for a given number of bits transmitted, kind of similar to error probability. Then we have the energy per bit, EB, is the amount of power in a digital bit for a given amount of time for that bit, and that's typically measured in joules. And then we have, of course, bit energy, which is energy per bit, is typically provided as a relative measurement to system noise. So it's commonly used, you see it as signal noise ratio. Well, this is bit energy per noise ratio in a sense. And we'll go over that a little bit more in the next slide. All right, so this slide is going to make you cringe in a few different ways. As stated earlier, we're mostly focused on the error probability more than the actual output of digital modulation. So we went ahead and provided you three different equations. We gave you the one for ASK, FSK, and PSK, the error probability itself, as well as the Q function needed to solve those problems. Now, be aware, some of your textbooks and some of your PE references may give you a Q function table in which you don't have to refer to these equations at the bottom. You may be able to just look it up in the table and plug and chug and get it done very quickly. However, in the examples, we're going to go ahead and use the Q function equation. That way you can see how I plug it in the calculator, as well as that way you get a feel of what the answer should look like. Also, something you may see in the bottom right, I have the actual what A means, amplitude, number of bits, noise, power, density, and so on. Noise power and energy per bit, EB and NO, those are both in joules. Watts per hertz is also joules. Those are going to be the same unit. So just be aware of that when we actually start doing practice problems. All right, let's start off with an easy problem. A digital modulation signal is transmitted at 115,200 bits per second at 0.5 watts. After receiving the full transmission, you discover 10 errors out of 2 megabits. Determine the error probability and the bit energy. So the first thing we want to find out is error probability, which is P of E. Look at the equations to the right. Let's see what we got. We have number of errors, bits, and probability. So the first one we're going to be using is this equation right here. So right now we're looking for the errors equals the number of total bits times the probability of error. So we have errors, which is 10, equals number of bits, which is 2 megabits, times P of E. Well, that's pretty simple. We're going to divide both sides by 2 megabits, and that'll give us P of E. So 10 divided by 2 megabits equals, chug that in our calculator, is going to give us 5 times 10 to the negative 6. So for the signal you have here, this is the probability of error that you're going to have out of the number of bits you put in. So out of 2 megabits, you're going to have a probability of error of 5 times 10 to the negative 6. All right, so that was an easy one. So this one, we'll just put it up here, times 10 to the negative 6. All right, now we want to find bit energy, which is E of B. So look at the equations to the right. We have a few we can work with, but I'm looking at, we have a bit rate and then we have power. Well, I can kind of actually find it using this guy right here. I'll tell you what, I want to clean this up real quick right here. Or here's what we have. We have the bit rate, which is 115,200 bits per second. And then we have power, which is 0.5 watts. Well, for this equation, I need time, and this is in bits per second. That's your rate. Well, to find time, it's very simple. It's going to be time equals 1 over your bits per second. And that's how we're going to find time. Very easy. So we're going to take 115,200 bits per second, and we're going to find the reciprocal over that one. It's going to give us an answer of 8.681 times 10 to the negative 6 seconds. So now we have our time. So if we actually plug and chug that in our little equation up there, it's your bit energy equals time, which in this case is 8.681 times 10 to negative 6 seconds, times, and we already have power, PT, which is 0.05 watts. So it's 0.5 watts. Again, another easy one. We're going to plug and chug that in our calculator. It's going to give us an answer of 4.340 times 10 to the negative 6 joules. And that would be our bit energy. So I'll just go and put it up here. Not every one of these has got to be hard. We have to start you off at least with an easy problem to get your feet wet. Now we have a little warm-up problem here. Let's get into a harder one. All right, now we're going to jump into the deep end of the pool. This one is going to have a lot more to it than the last one. So for this one, we have a keying signal is shown below. Populate the signal equations and find the error probability. All right, what I mean by populate the signal equations, populate these guys right here. This is what we had in the earlier slides. So we're going to have to identify our keying signal before we move on to actually find the error probability. So let's look at this signal. It looks like we have a binary code of 0010, and we have a wave reflecting that code. All right, so now we need to determine which keying signal is it resembling. Well, right now, in between 0 and 1 and 1 and 0, I'm not seeing any change as far as amplitude. So AS key, Amplitude-Shift keying, is mostly unlikely. As far as the phase of these signals, I don't see the phase shifting as well. The only thing I see shifting is the frequency. We're going from a low frequency to a high frequency when you're going from 0 to 1 and 1 to 0. So if I had to guess, it's going to be this guy right here. This is a frequency shift keying signal. For frequency shift keying, it has amplitude, cosine, and then your first frequency with time. And then for the next set, it's going to be same thing, amplitude, cosine, your second frequency, time. So those are zeros, those are ones. I think that's very simple. First thing we need to find is the amplitude. Well, amplitude is going to be your peak in this case, so it's 1, 2 millivolts. So for amplitude, for this one, and I'll just actually put it right here since we have room, it's going to be 2 millivolts. And always pay attention to your units. Sometimes it may be given volts, sometimes it may be microvolts, but this one's millivolts. It's going to be for both amplitudes, so that's pretty simple. Next, we can actually find our frequency, which is these guys. Just as a quick reminder, when you're trying to find this, it's 2 times pi frequency. So once you find your frequency, you'll be able to fill this guy in right here. And this is in radians. So let's find our zero first. Well, let's look at one full wave. So we have starting at 0, and you have one complete cycle at 2 milliseconds. Well, if any of you remember the basics, your frequency equals 1 over time, which is going to be 1 over 2 milliseconds. And that's pretty simple. You plug and chug that one in your calculator. It's going to give you a frequency of, your first one's going to be 500 hertz. All right. And then obviously, I'll put it over here real quick. So your first one is going to be 2 times pi times 500 hertz, which is going to be approximately 3141 point, we'll say 6. Keep it simple. I think we can find our next one. Our next one, same thing. We're going to look at a complete cycle. So it looks like it starts right here, because if you look at this, it looks like our code takes up at least 2 milliseconds per change. So it looks like it starts and stops right there, right there, right there, and so on and so on. So looking at this one, starts right there. There's 1 cycle, 2 cycles. So in a 2 millisecond time frame, we had 2 cycles, which means it only takes 1 millisecond to complete 1 cycle of this frequency, which is going to be 1 millisecond. So for this one, it's going to be, tell you what, let me clean this real quick. So for the second one, it's going to be 1 over time again, which is going to be, in this case, 1 over 1 millisecond. So if you plug and chug that, that's pretty simple. It's going to be a frequency of 1000 hertz. And if we follow the same guidelines over here, 2 pi times 1000 hertz equals, and we'll go ahead and say that's 6,283.2. So for the first one, it's going to be 3,141.6. And for the second one, it's going to be 6,283.2. Now let's find t, because that's a pretty simple one. T is time, so that's the amount of time per bit. So how much time did it take for an actual bit to go through? Well, we have 1 bit here, 1 bit here, and so on and so forth. So how long does it take to actually cycle 1 bit? Well, looking at 1 bit here, we're able to do it in 2 milliseconds. So that's a pretty simple one. 2 milliseconds is the amount of time for that 1 bit. Again, very simple, because if you look down here, it's the bit duration. 1 bit, 2 milliseconds. So right now, you have all the variables needed to fill these equations out right here. Now, I don't have any room to put this in up here, so I'm just going to leave these right here. But it's pretty much where you put these numbers right in these equations, and that's your answer. So number 1 is done. Number 2, find the error probability. Well, let me clean this up real quick. Now, error probability for this one, same as the last one's PV. And we know this particular signal is a frequency shift keying. So we're most likely going to be using these equations right over here. So let's go over what we know. We know our amplitude, we know our time, and we even know our noise, because when we zoomed in, we actually determined the noise is 20 times 10 to the negative 10 watts per hertz. And that's also measured in joules. Again, remember, energy per bit and noise power are both measured in joules. So these two right here have the same units. Just remember that. So right now, I think we have enough information here to actually plug and chug this in this equation over here. So let me go ahead and see if I can make room over here. So P of E equals, and since I have my amplitude, my time, and my noise, I'm going to use this guy right here. So it's going to be Q, parentheses, and it's going to be the square root of amplitude square times time per bit, or bit duration, over 2 times the noise. And I'll see if I can populate this and make it look halfway decent. So it's 2 millivolts squared times time, which is 2 milliseconds, over, and it's going to be 2 times our noise, which is 20 times 10 to the negative 10, and that's watts per hertz. And obviously we're going to square root this bad boy. Just plug and chug that in our calculator is going to give us an answer of 2, which means, and I'll put it right here, our probability of error equals Q function, parentheses, square root of 2. Square root of 2 is pretty easy. It's going to be Q function, parentheses, 1.414, and we'll stop right there, 2. Tell you what, I'm going to clean this up right down here real quick. Now here's where the fun part comes in. This is where your calculator is going to have to do all the work, because for Q function, we're going to have to use that equation right there. However, if you're a little rusty on your calculus, that's no problem. Your calculator can do a majority of the work. So let me go ahead and populate it down here. That way you get an idea what you're going to be looking at. So Q of X, for in this case, Q of 1.4142 equals, and again, I'm going to mimic this guy down here. So it's going to be 1 over square root of 2 pi. And then for X, it's going to be this guy right here, because Q of X, X. So it's going to be, for this one, it's going to be 1.4142. And it's going to infinity. And obviously it's going to be E. And for time is not going to change. This is what you're going to put in your calculator. You're not actually putting a value there. Okay. Now for those of you, again, who are very poor at your calculus, we're going to show you how to do this in your calculator. It's going to be very easy. It's not going to be hard at all. Since we're on a time crunch here, let's let your calculator do all the work. There's no point in doing this by hand. We're going to pull out their calculator and we'll show you how it's done. We're going to use our Casio 115. Now here's where the tricks come in. First thing we're going to have to do is change our mode. So we're going to have to Shift, Setup, and make sure in math mode. So it's 1, 1. This will allow you to use this function right here. That's the whole point of changing the modes. So that's the first thing we're going to do. And then we're going to start inputting this in the calculator. First thing we're going to do is Shift, that guy right there, negative. Now we're going to use X. Since they have X right here, remember how we have T? We're going to use X. So it's going to be alpha, X, and it's going to be square divided by 2. All right, so that part's done. You're going to have to use your arrows here. And for this side, we're going to do parentheses, 1 divided by square root of 2 times, Shift, pi, and then we're going to close parentheses. So that one's done. Now here's where the interesting part comes in. I'm going to put my 1.4142. We can't put infinity right here. However, you can put a high number. Most people recommend just putting a very, very high number. I say just put in 100. So if you put in 100 right here, this will give you an answer close to if you put infinity there. So I'm going to put 100. Then I'm going to put enter. Now your calculator may take a while. This one actually went pretty quickly. However, yours can actually take close to 15 seconds. So you'll have a blank screen right here for about 15 seconds, and then it'll give you an answer. But for mine was actually pretty quick. So for our final answer, we have 0.07865, and so on and so on. So that'd be our probability error just using our calculator. And that was pretty quick. We didn't have to do any calculus, anything by hand. So our final answer will come out to be 0.078, and we'll say 7 for our probability. So this is the probability of error for this particular equation. So that's actually kind of high. That's actually looks to be close to 7 or 8%. of an error that might actually potentially happen. The most important key element you can take out of this particular example is how to use your calculator to find some of these answers, because your calculator is very powerful and you can find some of these answers very quickly just by plugging and chugging in there. You just got to know how to use it. All right, so right now that's our final answer. All right, let's move on to the next problem. For our last problem here, we have a little more real estate to work with. A PSK signal has an error probability of a Q function of 4 and transmits 72.2 megabits per second at 100 milliwatts. So we're going to determine the noise. So noise in this case is N of O. So that's what we want to find out. All right. Well, we know our bit rate, we know our power, we even know a little bit of our Q function. So most likely we're going to be using this guy down here. Well, with this information right here, like we learned in problem 1, we can find our bit energy just with these two guys right here. Because remember, our bit rate, we can actually use the reciprocal of that and find our bit duration. So let's go ahead and find that real quick. So we want our bit duration equal, so it's going to be 1 over bits per second. And notice how I use a little b, it's not bytes, it's bits. So in this case, it's going to be 1 over 72.2 megabits per second. And if we plug and chug that, that's going to be an easy one. So it's going to give us a time of 1.38, I'll say 5 times 10 to the negative 8. That's seconds. All right. So right there, we found our bit duration. And we already have power. So right now I'm going to go ahead and put it down here. Our total power equals 100 milliwatts. So we have bit duration, we have power. Now we can find our bit energy. So pretty simple plug and chug answer. That's going to be 1.385 times 10 to the negative 8 seconds times, that's going to be our power, 100 milliwatts. And that's going to give us an answer of 1.385 times 10 to the negative 9 joules. So I'll tell you what, see if I can fit this over here. E of B equals 1.385 times 10 to the negative 9, we'll put J. All right. So we found quite a bit there, and I'll put our bit duration over here too since we have time. 1.385 times 10 to the negative 8 seconds. And power is 100 milliwatts. All right. So I'm going to clean this up real quick and we can move forward. Well, again, we're going to look down here. We already know our Q function, and it looks like I have enough information to use it right here. So let's go ahead and bring it over here real quick. Let's say probability of error, P of E, equals Q function, parentheses, and it's going to be the square root of 2 times your bit energy divided by noise. Looking at this guy right here, we know this information right here equals 4. So we can kind of work backwards off of that. So let's see what we can do. We could say 4 equals square root 2 times your bit energy divided by your noise. Well, I think we can work with that. Let's see if I can populate that. So it's going to be 4 equals square root 2 times, and we're going to use this guy right here, 1.385 times 10 to the negative 9 joules over, and that's going to be our noise. Okay. Well, the first thing I want to do is get rid of this square root right here. Well, the best way to do that is go ahead and square both sides. And that'll get rid of that. So square both sides. 4 times 4 is 16. 16 equals, and I'll just bring it down here, 2 times 1.385 times 10 to the negative 9 joules over noise. Man, we're getting somewhere. This is actually pretty simple. A little cheap way of doing this, just a little algebra. You could swap these two around. So your noise is going to equal 2 times 1.385 times 10 to the negative 9 joules divided by 16. And that'll give us our noise. Plug and chug that in our calculator. Gives us a noise value of 1.73, and we'll say 1 times 10 to negative 10. And that's also joules. Or you could say watts per hertz, whatever you prefer. So that right there is going to be our noise. And all I did was just take this equation right here and just use a little bit of algebra and worked backwards. I didn't even have to pull out any calculus for this one. Hopefully there's enough information here to get your feet wet. If you have any questions, feel free to let me know, and I hope y'all have a good day.